Okay, so let's have a look at a typical carbon-13 NMR spectrum. Down the bottom here, you can see the units, which are ppm, parts per million. If you take a look over here, you can see that the scale begins on the right-hand side. So we're reading it right to left, unusually. In this spectrum here, we can see we've got 3 total peaks, which tells us there are 3 unique carbon environments, so a minimum of 3 carbon atoms. This peak over on the left at about 205 indicates the presence of a carbonyl carbon, a C double bond to O. And the 2 peaks on the far right, they don't have any oxygens or nitrogens or anything on them. They're probably just carbons with hydrogens. So the number of unique carbon environments or peaks gives us the minimum number of carbon atoms, but it doesn't give us the actual number. Taking a look at the same spectrum again, we can count 3 peaks, which tells us there are 3 unique carbon environments, a minimum of 3 carbons. The peak at 205 ppm indicates the presence of a carbonyl carbon. So what are some possible structures that could give us this spectrum? The first possible structure, 3 carbons with a carbonyl group, is propanol, the aldehyde. Another possible structure is propanone, the ketone, 3 carbon ketone. And though it doesn't look likely first up, another possibility is methylpropanone. This one has 4 carbons, methylpropanol. This one has 4 carbons, but it does actually possibly match this spectra. Having a look at methylpropanol, you can see these 2 carbons are actually identical. And looking at propanone, you can see these 2 carbons are actually identical. So in fact, propanone in the middle would only make 2 peaks on a spectra, and so it is actually not possible for this spectra, whereas methylpropanol would make 3 peaks, as both the circled carbons contribute to the same peak as they are identical carbons. So actually this one is not possible. A fourth possibility for the same spectrum is the molecule pentanethreone. Having a look at pentanethreone, the carbonyl carbon is responsible for the peak that's shifted to 205, indicated here. These 2 carbons circled are identical to each other, so they are going to contribute to 1 peak on the spectrum, and because the 2 carbons are close to the carbonyl carbon, their peak is the one that is also closest to the carbonyl peak. These 2 carbons circled here are also identical to each other, and so will contribute to 1 peak only. And because they are furthest in the structure from the carbonyl carbon, their peak is also furthest from the peak, making the carbonyl carbon. However, this one's not likely, and we do need to look at a couple of other minor things to tell us why that's so. We can get some of this information from our other spectra as well. In fact, the most likely answer for the spectra we've been looking at is methylpropanol. 3 unique carbons, and as you can see, the 2 peaks at the far right here are different in height, which possibly indicates that one of them has had 2 carbons contributing to it and the other one only 1. This matches with methylpropanol, as 2 carbons, the 2 CH3s, would show a higher peak, the peak on the far right, and the carbon with the hydrogen is responsible for that very much smaller peak. So we've given you a bit of an introduction to C13 NMR, and in the next video we'll be looking at those unique carbon environments in a bit more detail.